Okay, so we're going to get started on Module 2, and we're going to take a peek at our learning plan. So you'll notice here in our learning plan, we have the PDF of the PowerPoint presentation that is going to be the sections that will be responsible for in Chapter 3. So even though this is Module 2, we're going to be looking at Chapter 3 from our book. So this is the PowerPoint presentation. Before I go here, I just want to call your attention to the way that the rest of the module is set up. So you'll notice that we have session recordings for Module 2. If we go in there, right now, I don't have anything populated from this year. These are going to be the recordings from last year, okay? You can reference those if you wanted to, but the information we're going to be doing is going to be, what we're going to be doing for this year. So it'll be very similar. And then you'll notice that you have the two indented portions here are your practice problems and your second assignment. So Module 2 practice problems is following along with me for the examples that we have here to demonstrate how we're going to be, solving these types of problems, as well as the formatting and the requirements for your assignments. So these are, a good lead in to what you're going to be doing for your homework. Now, you'll notice that each one of these examples will be covering, and then you'll see that you always are going to be using AutoCAD for all of your vector diagrams, okay? So, so keep that in mind. That's why I'm asking you to have AutoCAD open, because we'll get some experience on how to do those types of problems, so you're prepared for then your assignment number 2. So quite a few here to do, but like I said, we're going to be doing our practice problems. We'll get you all set for what's going to be required for that. So let me just go back to our learning plan. I'm going to open up our presentation. And again, it's going to be Chapter 3. Chapter 3 starts on page 43 in your book. And the first section that we're going to be looking at here is section 3.2, and it talks about the difference between scalar quantities and vector quantities. So I'm certain that you've hit this along the way. Have you guys, well, you had, I think almost everybody, not everybody, but almost everybody's had me for statics. So in there, we talked about scalar and vector quantities. We used vectors all the time. But how many have had physics already? Has that been in your sequence where you've had physics? Okay, in physics too, you would have gotten experience working with vectors and scalar quantities. So a scalar quantity is going to be a quantity that can be sufficiently defined by one type of an element. So just one magnitude, for instance. So if we start looking at how long something is, or what the distance is from one point to another, we can just identify that number. So 8 feet long, 20 miles away. Temperature, how warm is it outside? 78 degrees. Or time, it took me 50 minutes, or we have a 50-minute long class. So whenever we can define it with one quantity, fully define it sufficiently, that means it's a scalar quantity. As soon as we need 2 things to fully define it. So for instance, a vector is going to be fully defined by magnitude, so how much that quantity is, but also adding direction. So when we start looking at distance, we're looking at, all right, it's going to be this many units long, 1.5 units long. That's its magnitude, but its direction is now 30 degrees from, whatever we're looking at. If we look at distance in terms of, let's say, on a map where we're looking at, okay, that's 25 miles away, but it's north from where I'm at. You just went from a scalar quantity, which would just be the magnitude, 25 miles away, but by adding the direction, you've now become a vector. Okay. Now, when we identify a vector quantity, we show it a little bit differently, and it's an important distinction. So first of all, in figure 3.1 on page 43, you're going to notice that we have an example of a vector. A vector, as we know, is going to have both magnitude and direction. So right here, the magnitude is how long that vector is. Okay, so you'll notice that it's 1.5 units, and sometimes it might be representing 1.5 miles, 1.5 pounds, 1.5 kips, whatever it might be. But in this case, they're just saying generic units. This is how long it's going to be. And then as far as direction, you'll notice that we have the 30 degrees there, but we also have something else. What is that something else? to identify its direction. And I'll look at the chat to see if anybody knows. What's the other thing here? We've got 30 degrees, but what's the other thing that is giving us an idea of the direction that this is going? Ben? Yeah, the arrowhead, right? So when we represent graphically a vector is not just a line. We're going to draw it to a length, but we have to have an arrowhead on it. Okay, something that students tend to, I don't know, forget to put on, I think, or they're like, I don't have to worry about the arrowhead. The arrowhead is meaningful, and it first of all signifies it as a vector quantity, but it identifies its direction. So we could have 30 degrees in this case going up and to the right, but we could also have 30 degrees going down and to the left. And if I don't have the arrowhead on that vector, I don't know which way it's going to be, and it has a very different effect on the body. Okay, so when we're representing vectors, and you will be doing that, throughout this chapter, you are going to be required to put not only if it's, not on a horizontal or a vertical direction, you have to put its angle, but you also always have to put the arrowhead on it. Okay. Now, when we draw our vectors, the length is going to be equal to whatever its magnitude is, and the angle along with that arrowhead is going to be our direction, which we just looked at this figure 3.1. Now we're going to be using AutoCAD to draw out our vector equations and solve whatever we need to. In some cases, it'll be resultants. In other cases, it'll be maybe some other things. But the CAD knowledge that you need in order to do the graphical analysis here for vectors is, number one, be able to draw a line to a specific length and at an angle. I know you guys all know how to do that. You're going to have the ability of inserting lines, maybe perpendicular to other existing lines, and that's going to come in handy later on in our next module, module 3, when we start looking at velocities. You might have to extend lines, trim lines, draw arcs, locate the intersections between two arcs or lines, measure lengths of existing lines, and then also measure an included angle between two lines, all of which you have, extensive experience with in terms of the experience that you've had here at WCTC already. So I know you're prepared for these elements, but if along the way when you're using AutoCAD, if you have any difficulties, I'm here to help if I can. Now, as we skip over to, just want to remind you, you're going to notice that we're not going to be doing each and every one of the sections here for the same reasons that I identified earlier. We're going to focus on the graphical solutions only. We aren't going to do the analytical here in kinematics. If you're a math lover and you're like, I really want to know that, sure, work it out alongside. And if you get a sense of satisfaction through that process, but I'm not requiring it for you guys, because again, you get to do this in a lot of different places along the way in the program. So we're going to stick to graphical. So that means that we're going to go over to section 3.8, which starts on page 48. So if you are following along with your book, page 48 is where we're at with this section. Now, when we want to perform a vector addition, what that means is we are going to be determining what is the net effect on a body that has maybe a couple vectors, a couple forces, something that is going to be, pulling on it. So we're going to be using the first method that we have here is called the tip to tail method. And that's when we are going to be adding 2 or more vectors to our elements. So the process here is we're going to take the tail of the first vector, and we're going to put that at the origin. Okay, so the tail means that that's not the arrowhead side. The tip is going to be the arrowhead side, and the tail is going to be the non-arrowhead side. Then the second vector is going to be relocated so that its tail is placed at the tip of the first vector. Okay, so maintaining its own magnitude and direction. So that's why we call it tip to tail. We're going to take the tail of the second one and put it at the tip of the first one. And we're going to continue with however many vectors there are that are affecting the body that we're interested in. And then we're going to, once we get to the end and we exhaust all the vectors that we are dealing with, we then want to determine what the resultant is. And the resultant is going to be the one force that can replace all of those other forces, but have the same net effect on the body. Sometimes we call this, it's the combined effect of the individual vectors. We can replace with just one. This sounds really familiar because if you had me for statics, you're probably remembering we did this kind of stuff. We solved vector addition problems, if you would, analytically, using the rectangular component method. We did that over and over and over again. Now we're going to do it, if you would, graphically, okay? Now, if we're going to represent a vector quantity in terms of an equation, so if we're going to add some vectors together and we want to find out what the resultant is, we would write the vector equation as we see down here at the bottom. So you're going to notice that we start with r is equal to, that's the resultant is equal to. And then you're going to notice it says A plus greater than B plus greater than C. But the operators that we have in between, this quantity right here, this plus greater than, that is considered the accepted symbol for writing an equation in vector format. We call it a vector addition because it's not an algebraic addition. All right. If you remember back from physics, we can't just take the magnitude of vectors that are not along the same line of action and just add their magnitudes together and get the final answer. Okay. We have to take their direction into account. Okay. So in order to signify that this is a vector addition as opposed to an algebraic addition, we use this greater than symbol, which kind of looks like an arrowhead, right? On the tip of a vector. So we see A plus vectorially B plus vectorially C. We can also change the order and have the same net effect on the body. So maybe we would want to start with vector C and then add vectorially B to it and then add vectorially A. Or we could also then do B plus A plus C. All of these, no matter the order that we vectorially add vectors, we're always going to get the same net effect. Okay. So for instance, if you're comparing homework with somebody and they did, a vector addition in a different order than you did, you're going to notice that you probably both have the same answer. Neither one is the more correct way to do it. It's just that it's a different order and we will always get the same net effect on the body. So the resultant will remain the same. So if you look at your final answers and you compare those, then you'll know that those should match. So let's do a vector addition. This is going to be example 3.5 on page 49. So we are going to be using AutoCAD. So if you want to pull out your AutoCAD and get that going, if you haven't done so already, we're going to be doing that, using it for this first problem. Let's sneak this over a little bit. Okay, so the problem statement here for 3.5, it states that we want to graphically determine the combined effect. That's going to be like adding them together. We want to vectorially add these together, which is going to be the velocity vectors of A and B. So A is right here on the left-hand side. B is on the right-hand side. Okay, as shown down here. So we want to add these two vectors together and we want to determine what is the resultant. Okay, so we are going to go over to AutoCAD. And I have my start file here open. And the reason I have my start file open is because I can use this here. I might not be using this, well, some of the letters I might use, but the symbols and stuff for kinematic diagrams, we're kind of getting away from that in chapter 3 here. It'll come back in our next module. But for right now, we won't worry about the frames or the sliders or the joints. What we're going to be drawing is going to be vectors. And because we have some additional layers here, I'd like to utilize those so I can see the different colors and the line types as needed for the vector additions. So let's vectorially solve for the resultant of A and B in problem 3.5. So the process that we're going to go through is we're going to first draw each one of these vectors as we see them. So you're going to notice that A has a magnitude of 59 inches per second, and it's going at 30 degrees up and to the right. And then B is at 30 inches per second, and its direction is going up and to the left, okay? So first of all, we're gonna have to draw each one of those vectors in the orientation that we see it. So what we're gonna do is we're gonna go over to AutoCAD, and this is where I wanna kind of make sure that you understand what you're responsible for and how these are going to look. So we are going to represent A as a line, okay? And I'm going to left click, and now I have it on ortho, so I am going to, I'm gonna turn off ortho, okay? And then what I'm gonna do is I am going to draw its length 59 inches per second long. Actually, I don't think how I want to do this. Let me see. All right. So as we're looking here, you're going to notice down at the bottom, you should have this polar tracking available to you. And then there's a little down arrow on the right-hand side. As we look at the angles that we're dealing with, so I'm going to go back underneath here, you're going to notice I have one at 30 and one at 60. So what I want to do in AutoCAD is I want to restrict the cursor to only go to specified angles, but I got to identify that angle first. So on the down arrow that's on the right-hand side here, we want to pick the one, and in this case, 30 and 60, we want to restrict it to snap to angles that are at a 30 degree, like if you would, in 30-degree increments. So I'm going to click on this one right here, okay? And what's going to happen is you make sure that your polar tracking is on, and you're going to draw a line. See, start over, draw a line from a point. And now when you move this, you're going to notice that when you get close to that 30-degree increment, it's going to actually snap to that. Okay. So your polar tracking has to be on. It has to be set to whatever the values that you want it to be. And in that case, we picked the 30, 60, 90. So now as long as I'm on that 30-degree angle, I am now going to be able to key in my 59 for the length. Okay. And it's going to be quite big on here, and I'm going to hit escape, and I'm going to zoom extend so I can see my full line. Okay. All right. So now I have this first one. It's the right length, but I need to put an arrowhead on here. Now, you might say, well, I could use a leader. I wouldn't monkey around with AutoCAD to try to get your leaders to have the right size arrowhead, because you're going to be sitting here forever trying to get it to be perfect. For the problems that we're doing, to call out the arrowhead or the direction, all I want you to do is take a line, and you're going to start at the start of it, or at the tip of it. I'm going to turn off polar tracking right now. And I just want to represent a line that I can see that, oh, that's the arrowhead. Then I'm going to do another little arrowhead here. Does not have to be exact, but I know that this line is going up and to the right. So you don't need to do leader arrowheads on these vectors, okay? Because again, then you'd have to go in, you have to change the scaling and play around with that and see if it's right and blah, 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 blah. We are drawing these again, not for anybody's eyes except for ours, to graphically represent and show, you know, solutions to problems. So this is our vector A. Now, we always have to label our vectors. You do not need to add the dimensions for given quantities. For instance, I'm not going to put in a dimension for the 30 degrees, and I'm not going to put a dimension for the length, because the resultant we will do it for, and you'll know if you did it correctly by getting the correct resultant. Does that make sense to everybody? Okay. So you don't need to label these. The only thing you need, you don't need to dimension these. The only thing you need to do is label its name, if you would. So we're going to call this one A. Okay. So we do have an A already identified here that we can use as the label. So all I'm going to do is I'm going to move my A, zoom back out, from where it's at up to, I don't know, right about there. So I have mine, you can kind of see it. It's right there. It's tiny. So if I would want to print this off, or if I would want to take a screenshot and be able to see this, I'm not going to be able to make out A. So all I'm going to do, I'm going to make this as easy as possible. I'm going to scale that A. And I'm going to select just the A. I'm going to hit enter. And then it wants to know the base position. I would put it really close to the middle of A. And then all you're going to do, oops, did it not? Hold on. Let me try it again. I thought I was following it along. Scale, A, enter, base position. There we go. Now I've got it. And all I'm going to do is I'm going to just pull out until I feel like the A is big enough so that when I take a screenshot, it'll be visible. Okay. So now I've got my A large enough in comparison to my, my vector. Now I'm going to draw the next vector. So the other vector is B. It's going up and to the left. So I'm going to do that very same thing. I'm going to do a line. I have to turn back on my polar tracking. Okay. And this line is going to be, now if I look here, notice that my angle comes from the standard 0. So this is going to be 60 degrees from the other side. So that means that it's going to be 120 from the known 0 or the known 0 degrees. And then my length is going to be 30. So I can key that in along that line. Then I'm going to hit escape. Then I'm just simply going to arrow in, and I am going to, now this is, that polar tracking is on. I want to turn it off so I'm not tied to the vertical or the horizontal. Okay. And then I'm going to do another one similar like that on the other side. So there's my arrowhead. And then now I need to label this B. So since A is already the right size, I'm just simply going to copy A. And I'm going to move it over to the other arrowhead. And I'm going to relabel this as B. Okay. All right. So now I have the two vectors identified and redrawn to scale at the right angles. And I really don't need any of this stuff from that start file, so I can get rid of that. Also rename it so that it's example. And this is 3_5. Save, there we go. Okay, so now what I have is I have a duplication of what we see right here. So I drew my vectors to scale, and I labeled each one of those. Now what I want to do is I want to do the vector addition to find the resultant of those two forces. So I'm going to go back to AutoCAD. Now, as we said earlier, we are going to be adding these tip to tail, but we need to have an origin. So we need to identify where we're going to start. So you pick one of those vectors. Are we gonna add A plus B or B plus A? We'll start by adding A plus B. So that means that A's tail, okay? So A's tail is going to be the side of the vector that does not have the arrowhead. This is going to be our origin, okay? So that means that I need to identify the origin with a crosshair. So I'm simply going to put vertical and horizontal lines to represent, where we are starting. So you always have to show me your origin, okay? Your origin is going to be the start. So the tail of the first vector is going to start at the origin. So identify your origin. Then what we're going to do is once we have our first arrowhead in position, we're now going to move the second arrowhead so that its tail is at the tip of the previous one. So the tip is the arrow side, the tail is the non-arrow side. So I'm going to move B, select that. I'm going to go to its endpoint, and then I'm going to move that tail to the tip of the previous vector. Okay. So I've successfully added A plus vectorially B. Now, if I would do A plus B algebraically, A was 59 units long, 59 inches per second, and B was 30. So if I would do that algebraically and I would add those two numbers together, I would get 89, right? So that means that I should get 89 for my resultant. Will I get 89 for my resultant? Everybody who got me for statics should better be saying, no way, Jose. I'm not, because It's not an algebraic addition. We're taking both magnitude and direction into play. So to find my resultant, I am going to start at my origin with the tail of the resultant, and the tip is going to go to the tip of the last vector in my diagram. So I am going to change my layer to object 2. I am going to draw a line starting at the origin. Make sure you get the endpoint of the origin, and then I'm going to draw it to the endpoint of the last vector, or the tip of the last vector that I put, you know, in my diagram. And now the tip of the resultant will always point towards the very last arrowhead on the vector diagram. So that means my arrowhead is out here. Okay. So if I scooch in here, I need to add an arrowhead of my resultant. And I usually make it, if you would, bigger than what's here. Now I know we're not seeing the dashed lines. That's because if we would go in, we would see them. It's just bigger. It's totally fine. If you want to change the LT scale, go ahead. I'm not too worried about it because you'll be taking a screenshot and I'll see it as green. So I'll know that that's the resultant. And you're also going to label it the resultant in just a bit. So notice that my arrowhead is pointing at the last arrowhead in my thing. If my arrowhead was pointing down and to the left, that would be wrong. Okay, the direction would be wrong. The resultant, remember, is going to have the same net effect on the body as the combination of, in this case, the 2 vectors. So right now I'm going up and to the right, and then I add up and to the left a little bit. But what the resultant is telling me that it still is going up and to the right. That's going to be the tendency of, if you would, the pull on the point that we see down here. So now let's label the resultant. So I'm simply going to copy either your A or your B over here to your resultant. And we're going to change that to the R. Okay. Do a quick save. And then we need to determine the magnitude and direction of our resultant. So the magnitude of the resultant, I am going to change this to notes, and we're going to put an aligned dimension on it. You can't do a linear dimension because it's not a fully vertical or horizontal dimension. It's along an angle. So we're going to do an aligned dimension. We're going to go from one endpoint to the other, and we're going to dimension it out right about there. Okay. Now, as you can see, if I would take a screenshot here, I would not be able to make out what that value was. So we are going to need to go into annotation, dimension style manager, modify, and on the fit tab, we are going to change the overall scale. Okay, this is the scale for the dimensions. We're going to change that. We need to make it bigger. So we're going to say, I don't know, we'll start by, I'm going to go 10 and we'll see. And this is kind of like the experiment you have to do. You're going to set as current. You're going to say, okay. And oh, that was pretty darn good. So times 10, I would maybe even make it a little bit bigger. It doesn't have to be perfectly the same size as the other things, but when you take a screenshot, remember, I've got to be able to see it. So I'll go back in there again. I'm going to do that dimension style, modify, fit tab, and I'm going to change this to 15. Okay, make it a little bigger. And yours doesn't have to be exactly, but it has to be big enough for me to see. Okay. Now, the other dimension that we need to add is we have our magnitude. We need to do direction. Even though we have the arrowhead on here, remember, this is not at a vertical or a horizontal position. So we need to add the angle. So that means that I'm going to put an angle dimension in. And because we already changed the size of that dimension, it should be fine. So I am going to go from my resultant, but I'm going to go to a known coordinate. So I'm not going to go to another arrow. I'm going to go back to, if you would, the horizontal line here. And I am going to be at 57 degrees. Okay. Don't go from one of the other vectors. You're either going to go to the vertical line or the horizontal line, right? And now what that means is my resultant is 66.2 inches per second at a 57-degree angle from horizontal, okay? And it's going up and to the right. So if we look back at our example, you're going to notice that they go through that very same process. They show us their AutoCAD. They, you know, and this isn't wrong. They're showing the direction going up and to the right, rather than putting the arrowhead at the very end where they all kind of intersect. Sometimes it's hard to determine which one is which. They just kind of push them along, you know, away from the endpoints. So they rounded just to 66. Ours would be 66.2. So 66 would be correct. And then you're going to notice that they have a 57-degree angle. Okay. Now, what else do we need to add? The very last thing that we need to add is going to be our vector equation. All of your vector diagrams need a vector equation. So you're going to notice here that they have R is equal to A plus vectorially B. So you need to label that. That tells me what was the order that you put this in. So if we go back to AutoCAD, because I already have A, B, and R scaled, I'm simply going to do a copy. I'm going to take R, I'm going to put it up over here or somewhere close to the diagram. Excuse me. And I am going to double click on this. And now I'm going to write that vector equation. So R is equal to, and in my case, I started at my origin with A. So A is the first vector in the vector equation. So this is going to be A, and then it's going to be space plus, and then you have to put the greater than symbol. That's going to signify that this is not a regular algebraic addition. This is a vector addition. And then you're going to put the next vector in order, the one that was added to it, and that was B, okay? If you write this vector equation as B plus A, it is incorrect because that is not the order that you drew it in. Your origin specifies the start of. Now, I like to also think of the origin as the equal sign. So I'm going to click out of here. So when we look at our equal sign here, we always have a left and a right side. When we look down here, if that equal sign is our origin, do you see how the right side is the A plus B? And then if we go back to the equal sign and we figure out where R goes, that's kind of like the left-hand side of the equation. And that's why we take the tail of each one and we meet it at the endpoint because they have to be equal. So R has to equal what's going on with A plus B. So they all end out here. That's kind of like the end point, if you would. So, so they have to be equal. Are there any questions on this one so far? Okay. You'll notice that they did the second vector addition, and all I'm going to do is just kind of show you this. I believe that that this wouldn't be too hard to see, but you'll notice in this case on the right-hand side, they did B plus A. And the whole point here is that they end up with the same value. You still get the 66 for your resultant, and you still get the 57 degrees. Okay. So that's why no matter what order you added in, you'll still get the same resultant. You just have to let me know. So I know that you know how to write the vector equation for what you just did. Okay. So your diagrams are going to include what we see here. Each one of your vector needs a label. So in this case, we had an A and a B. We did not put their dimensions on because again, it would clutter this up. And by doing the resultant and adding the magnitude and the direction there, so the 66 point, I have 4 decimal places. You might ask, how many decimal places do you want, Kelly? I just leave it. I normally have 3 or 4, I think is good. You're going to see the answers sometimes are rounded to different, values. As long as yours are rounding to that, I'm totally fine with that. So again, theirs came out, they left it at 66, 66.2 would be 66 rounded to 66. So that's correct. And then the 57 degrees. So the labels for magnitude and direction need to be on the resultant, okay, not on the other ones. By getting the correct resultant, I know that you drew A and B correctly, okay, so you don't need those in there. And then also make sure that you add your vector equation to represent what you saw here. So this one would be your example 3.5, okay. So for handing in wise, it's going to be a screenshot just like we see here, including the vector equation. Right. All right, so that was example 3.5. Let's do another one, example 3.6. This time we're going to have a couple extra vectors to deal with. So it says determine the resultant of forces A, B, C, and D. And we're going to do the vector equation or the resultant equation in two different forms, okay? We're going to do, or I should say in two different orders. So if we go over to example problem 3.6, this is at the top of page 50. And it says here, we want to graphically determine the combined effect. We want to determine what the resultant is. That's what it's saying of the vectors that we see here, A, B, C, and D. So first things first, we need to draw each one of these vectors to scale at the angles that they are. So what we'll do is I'm going to give you time. You don't have to watch me do each one of these. You saw how to do that one, but we're going to do a new example, a new start file, and then we're going to, you know, kind of go through that same process. So go ahead and I'm going to save here first. I'm going to do an open. There we go, open. I'm going to start with that kinematic start file, and I'm going to start by drawing all four of those vectors. Save as. This is going to be example 3_6. Okay. And then we'll compare in just a bit once we get those four vectors drawn. Now, again, you don't have to go in and label these. I am just checking to make sure I've got the right length. Oops. before I start adding these, because I want to be sure that I got the right. Especially the angle. That's the only thing I'm really worried about. It's the other ones I'm pretty confident on. Now, I am going to tell you there is an answer key for the homework problems. So you'll always know, just like you do with these examples, as you do the problems, did I do it okay or not? So you can compare to the answer key, your final answer, and that'll confirm that you did it correctly. Okay, how many need some extra time to get the 4 vectors? Anybody? All right. If not, then we'll move to our next step. So the next thing that we're going to do is we are going to add these together. Now, in the book, the first way that they add it together is in alphabetical order, A plus B plus C plus D. So again, we're going to do the tip to tail method. Now we are going to do it 2 different ways. So at this point, before we start moving our vectors around, what I encourage you to do is just copy all 4 of these vectors so that you have another fresh copy to move around for our next order to do the resultant. So the first one, I'm going to use these, this first set. And what we're going to do is we're going to add those in alphabetical order. So you'll notice that A is our first one. So I am going to identify at the tail of A, this is going to be my origin. So make sure that you add here, object line layer, make sure that you add kind of like a crosshairs to represent the origin of our diagram. I will be looking for that. You will lose points on the assignment if you don't add that, okay? So I need to know where you're starting. And I want it to be consistent with where, you did your addition. So we're starting with A. A is our first one. So at the tail of A is going to be our origin. Now, our next vector that we're going to add here is going to be B. And I'm going to move B now. So you can either use the move up on top or M enter, and you're going to select the full vector with its label. You're going to hit enter. And then now we're going to start with its base position. Its base position is going to be the tail of B, and we're going to move it to the tip of A. And there it is. Okay. Make sure that the label's on there, and then also make sure that, you're hitting your object snap so you get to the endpoints here. The next one then is going to be adding C to the end of B. So we're going to move, select vector C and its label. Then we're going to grab the endpoint, the tail of C, and we're going to add it to the tip of B. Okay. And then lastly, we're going to do that very same thing. We're going to move D, enter. Base position is going to be the tail of D, and we're going to move it to the tip of C. So we have now added A plus B plus C plus D tip to tail. So we're going to then identify our resultant by taking a line from the origin, and it's going to end at the endpoint or the tip of the last vector. Okay. Its arrowhead, the resultant's arrowhead will also be at the tip of the last vector. So this is the tip of our resultant. Okay. So the net effect of those four forces is up and to the right. So if we would replace those four with one force, that's our resultant. And then we want to label it. So I'm going to put my D over here. This is my resultant, R. Okay. And I'm going to do a quick save. And in this case, I'm going to, I'll do my dimensions first. So I'm going to put my node in place here. I'll add my angle dimension first, since my angle is up. It doesn't matter which order you do these in, obviously. And I'll put this out here. I can't see the number, so I'm going to have to go into Dimension, Style Manager, second one down, Modify. And I'm going to say 25. We'll see where that looks. So my scale is 25 on the Fit tab, set as current, close. Not big enough. So I'm going to double click it. Oopsie. I'm going to go back up. Oopsie. Annotate. Dimension Style Manager. Go right back in. It should remember that you're on that tab. So I'm going to say 60 because I think it's more than 50. Okay. Set as current and close. Closer. I'm going to go even a little bit bigger. Oopsie. Why am I clicking on the dimension? I'm going to go to Dimension Style, Modify, and I'm going to set it to 75. Okay. Set as current and close. And that's pretty good. That way, again, gauge it by how large or small your screenshot will be and that you can see it in there. Then I'm going to add the aligned dimension to the endpoint of the resultant. And there it is. Okay, so it's 520, probably 1. So we'll see what we end up getting in our example. So the last thing we need to do is to add the vector equation. So I'm going to, it's going to start with R is equal to, so I'm going to just copy my R. And I'm going to put it up at the top here, should be good. I'm going to double click and it's going to be equal to A plus vectorially. So we have to add the greater than sign, plus B, oopsie, B, plus greater than sign C, plus greater than sign, greater than sign D. Okay, so you have to have your equation that represents the order for which you added them in. You have to have labels on each one of your vectors. Each one of your vectors has to have arrowheads, and you need to have dimensions for the magnitude and the direction, angle and the magnitude, or the length of that vector, dimensioned so that I can see it. I don't want anybody to have a small little dimension and then you just like, write in what that value is going to be. No, no, no. I want to see it as a dimension. So you have to go in and do the scaling on that Fit tab. Okay. All right. So this is the first part of this example. The second part of this, before we go further, let's compare our numbers. I'm sure they're correct. So if we go down here, notice they got 521 for our resultant, the magnitude. We are not doing it as a note. You're doing it as a dimension. And then they got 68 as the angle. So if we go back here, ooh, I got 69. Ooh, let's see here. I wonder if it was 68 point something. We don't really know. Well, we'll see if the next one comes out. We're really super close, but and I don't always trust their information in the book here because it's been known to make some mistakes. All right, so the next order that we're going to do this in is I'm going to copy this equation right here. So I'm going to copy, and I'm going to just grab the vector equation, and I'm going to pull it over here, and I'm going to change the order to match what we're going to be doing in the second part. And this one is going to be B plus vectorially C plus vectorially, A plus vectorially D. Now, even though we're doing this in a different order, we're using the same vectors. So they should come out to be the same resultant. And that's what we're really kind of testing here. So we're going to start this time with B. as our first vector, which is going to come off the origin. So I'm going to go back to my object line. I'm going to add in, now again, not a, exact number or an exact size for what the origin needs to be. It just has to be noticeable by me not having to zoom in to see it. So if you say, oh, my origin is there, you just can't see it because it's zoomed out. Well, then make your origin bigger so that when you do the screenshot, we can see the origin. That makes sense to everybody? Okay. So we're going to be B plus C plus A plus D. So I'm going to move then my C, its tail to the tip of B. Then I'm going to move A, tail to the tip of C. And then I'm going to move D, tail to the tip of A. That's good. Okay, so that means the right-hand side of my equation is all set. I'm going to go back to the origin. I'm going to use object to line style or layer. I'm going to start back at the origin, and then I'm going to put my resultant line to the endpoint of the very last vector. And then I'm going to zoom in. My arrowhead is going to go to the point where the last vector's arrowhead is. So these are going to be like right here. Okay. And now I'm going to label this R. Go down here. And this is going to be R for my resultant. Now, lastly, I have everything labeled except I need the magnitude and direction for my resultant. So the annotation should already be set up. So I'm going to use that align dimension to get the magnitude. Okay, I'm going to put it on the right layer. So I'm going to select it, put it on notes, and I'm going to select notes and have that as my active layer. That is the same number that we got over here. Yep, exactly the same number if you look for the magnitude of that resultant. And then as far as the angle, I'm going to go to the horizontal of my origin to my angle, and I'm getting 69 again. Okay. So I'm confident. They have 68, we have 69. It's super duper close. All right, so this would be what you would want to do, and including the equation for the screenshot, for example, 3.6. Now, if you want to move these closer together and get them on the same screenshot, just make sure that your screenshot, I can read all of the text and the labels that you have, and I can also see the arrowheads. So if that means that you have to do them in two separate, that's okay. All right, so that's our second example. Any questions so far? Any questions on adding vectors? How many have had experience adding vectors? Those of you who have had statics, you guys have. Okay. So good. I'm gonna do a quick file save, and then let's get back to our PowerPoint. The next one here is going to be vector subtraction. Okay, vector subtraction. So vector subtraction is a little bit different in that now we're going to notice that in this case, we've got a resultant. And what we're going to do is we can say A minus B. Okay, and notice that our operator changes here from an addition symbol to a subtraction symbol. Now in statics, we didn't do any vector subtractions. Have any of you done vector subtractions in any other classes? Did physics do it with you guys or no? Sometimes they do. It depends on the subject. You don't remember? Vector additions, I know, are the more common one, but this is vector subtraction. So we'll be practicing this. This, like I said, might be new to some of you. Now, just like algebra operators, we know that when we have a negative value on a variable, it's kind of like adding the negative version. So we can also write it like we're going to add the negative of B. Or we could just say if we, multiply these two together with the imaginary one in front, this would also simplify as A minus B. But if we expand it out, it's adding the negative value of B. Now, what does this mean to us? So there are two different ways that we can handle this. And we're going to look at page 55. This is our vector subtraction page. And in the first column, figure 320 shows the negative version of a vector. The negative version of a vector is just changing its direction 180 degrees. So for instance, if the positive direction of A is identified as going up and to the right, the negative direction is going to be on that same line of action. Notice that both of those vectors are parallel, but the only thing that changed was the arrowhead is now on the opposite side, which is 180 degrees from where it was at. Okay, so this is the positive version of the vector, and this is the negative version of the vector. Okay. Now, down here shows us two ways that we can deal with vector subtraction. So if we look, we have two vectors, A and B. These are their positive directions, meaning that A is going up and to the left, B is going up and to the right. And what we want to do is we want to subtract B from A, okay? B from A. Now, we go back to our PowerPoint presentation. You'll notice here that we have A minus B. So I want to subtract B from A. But the second equation in back of the resultant here is saying, oh, I'm going to add the negative version of B to A, okay? Now, when we do a vector addition is always going to be tip to tail, okay? So we're going to do this one first. We're going to see how this one works out. So if we go back over here, you're going to notice that C is going to be J, which is our resultant, is going to be equal to A plus vectorially the negative value of B. Okay, that's going to be this arrangement right here. So if we start with our origin, we're going to have A in its normal position. It's a positive value. But then we're going to add to it, tip to tail, the negative B. So B was in its positive position going up and to the right. Its negative direction is going down and to the left. So now we're going to take that negative direction and we're simply going to add it tip to tail to A. So here, notice that here's the tip of A. And now we're going to do the tail of the negative B. Negative B is going down and to the left, so the tail is there. Its arrowhead is going to be here. And then we're going to go back across the equal sign, and J is going to be equal to that value. Okay, does that make sense to everybody? You see how that happened? Okay, and we'll look at this a couple more. Now, the other way that you can do it, but you aren't going to. Okay, they show it in the book like this, and they flip-flop. They do it one way sometimes, they do it another way the other. This right here is the way that I want you to do all your vector subtractions, because it's an extension of the same process that we're using for vector addition. Vector addition is always tip to tail, always. And all this is doing is it's taking, oh, A minus B, well, we're going to add the negative version of B. So we're still doing tip to tail. We're just switching the direction of the arrowhead 180 degrees. Now, in the next 30 seconds, I'm going to explain the other way to do it, and then you're going to forget it. But I want you to see why I discourage this method. So the one on the right, here's our origin. This is going to be A minus B. What do you notice about the A and the B here? The tails are, or the tips are together. So vector addition or vector subtraction is basically taking the tips and they're putting them together now in the opposite direction. So instead of going tip to tail, you're going tip to tip. Okay. Now that we've done the right-hand side of the vector subtraction, we go back to the origin, and now your resultant's tip is going to go to the tail of the last vector. So it's kind of like it took everything that we learned before, and it's like the opposite world. And I think it's hard to keep track of that. This way, if we do, we're going to add the negative value. All we do is we change the direction of B 180 degrees from its positive value. And now we simply add it tip to tail like we normally do. And our resultant is still going to have the tip going to the last vector. So process-wise, it stays consistent. The only thing that you change is when you see that there's going to be a subtraction, you just change the direction of that arrowhead, and now you move along like a regular vector addition. You're just adding the negative version of it. Okay, does that make sense to everybody? So that's why this to me gets confusing. Like, okay, I put the tails together and the tips together and which one I'm doing, whether I'm a resultant or if I'm the regular vector. To me, that's a lot to keep track of. This just changes the direction of one arrowhead. And now we're going to continue to add the negative values. So it's still a tip to tail. And then the resultant is treated the very same way as well. Okay. So that's why we're gonna do it in this method. And we're gonna see in their examples, like I said, they're going to not be super consistent. So that's why we're gonna stick with one version. So our next example is gonna be 310. I'm just gonna go back to our PowerPoint. That's what we should see here, example 310. So let's go back to AutoCAD. We're gonna start a new file. So this is gonna be, you can save that if you need to. And then you're going to open up your kinematic start file again. And we're going to rename it, save as. This is going to be example 3_10. All right. And then now what we're going to do is we are simply going to go back to the book. And you're going to notice here that we want to graphically determine the resultant of subtracting the velocity vector B from A. So this is going to be an A minus B. And the equation is going to be J is equal to A minus B as we see here. So they're giving us the positive directions of A and B. So go ahead and draw the positive versions of A and B in AutoCAD. And then we will go from there. So just draw the positive directions as we see them there of A and B. So A, that's 9 degrees. Oh, crap. Well, that means I'm going to have to rotate. So there's not an even increment that we can change that to. So I'm just going to draw a horizontal 32 long. Oopsie, come on. Line. Oh, my number's lock isn't out, and that's why. 32. Oops. Now I didn't have it pointed in the right direction. And then I'm going to rotate this. Turn ortho off. It's going to be -9. So I'm just drawing mine vertical or horizontal, and then I am rotating to the angle it needs to be. So it's going to be 66. Isn't it? Okay. So you should have two vectors, A and B, in their positive form. Might make this just a little bit bigger. just to ensure that I'll be able to see it on your screenshot. Okay, so there are the positive values of my A and my B, right? Now, I'm going to go ahead and I'm going to write the equation above so that I can kind of reference it as we move things around. So I'm going to double click on this. It's going to be R is equal to, and we're going to have A minus vectorially B. Okay, that's what we're going to have. So that's my vector equation. And now I want to perform that. So I'm going to change this right here just so that you have it as a reference. So if you want to add it, you can. It won't be wrong if you don't. I'm going to do A plus vectorially, and I'm going to put in parentheses the negative B. Okay. This is what we're actually going to perform. We're going to add the negative direction of B. So now what that means is I'm going to change the direction of B 180 degrees. So rather than going down and to the left, it's going to go up and to the right. So I'm simply going to, and you can do this on the very same vector, get rid of the arrowhead down there, and then you're just going to redraw it in to represent it going up and to the right. And then you're going to change the designation of B to be negative. That's it. Make sure you do that. If you don't change the designation, then it's thought of to being positive going up and to the right, and that's not the case. Okay. Bless you. Now, how we're going to perform this is we're going to do, remember the equal sign is right here. So that means that my first vector to the right of the equal sign is going to be where the origin is. I'm going to make it's kind of bothering me. My arrowhead on my A isn't as big as the arrowhead on my B. So doesn't have to be perfect, but relatively close. So I am going to add the origin here, designation. So just like a crosshairs, that's large enough. So when I do my screenshots, I see it. There's my origin. So that means that's going to be the positive A. There's nothing in front, so positive is assumed. Plus vectorially, tip to tail, the negative B. So I'm going to move my B, the negative B, so that its tail goes to the tip of the previous vector. And then I'm going to put my B over on this side, because my R is going to come up in here. So you should have your negative B label on there, and it's going up and to the right. Then I'm going to change my layer, and I'm going to add in a line from the origin to the tip of my negative B vector. And this is going to be the arrowhead or the tip of my resultant. So I'm going to put my arrowhead on it. Arrowheads never go back to the equal sign. The arrowhead is always going to go to the last tip that you specified. And then this is going to be my resultant. I'm going to move this because I know I'm going to have to. I'm going to have to add my dimensions. So I'm going to go to my notes layer. Ooh, Tyler. I'm sorry, I'm seeing that you have something. Why don't you use the tab to enter the angles? Oh, I could. Yeah, you can use the tab. Yeah, that's fine. You can. I just never did it. I didn't think about it at that moment. So yeah, that would be the better way to do it. Faster, more efficient. So I'm going to start with my angle. Go from here to horizontal. Do not go to another vector at an angle. Obviously cannot see that. So I'm going to go to my dimension style manager, modify. Let's start with 50. Okay. Set as current and close. Oh, perfect. I'm not even going to change that. That looks good to me. Okay. 94 degrees. And then I need to do an aligned dimension from here to here. And that is 65.47. Well, that's not good. Did you guys get anything different than me? In the book, they've got 56.8 as the length. Did you guys get that? You did, then I did something wrong. And 99? Let me look. I've got to go back and see. Yeah, that's okay. I had that as my endpoint. Let me just double check. So I'm gonna do my aligned. Maybe one of my links isn't correct. This was 66. Oh, no, you know what I did? I did 66 long. It was supposed to be 56. Do you see that for my B? That's why mine is different. So are you guys getting 56.8 for the length? Yeah, and you're getting 99 here. So this dimension of mine is wrong. I'm not gonna redo this one. You guys are expected for yours to match. Did you guys get yours? Yeah, you got 56. Yes, 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 yes. And 56.8, it matches exactly what they have here. So make sure that you have these two numbers. I glanced over and I used the 66 in both the angle and the magnitude. So my fault, but at least we know. At least we know. So you guys are going to be held to a higher standard. Okay, any questions on the process though? Does it make sense? Okay, let's do another vector subtraction, and that'll be our last example for the day, which will get you started on the homework, okay? So if we go to our next example, this is going to be example 11.3. It's at the bottom of page 56. And we're going to be doing the following equation. J is equal to, which is going to be our resultant, A minus B minus C plus D. So if we go to our book, here are the magnitudes and directions for each one. Try to get this on here so you can see. For each one of our vectors. Try that again. There we go. So I'm going to try this time to do it correctly. So I'm going to do a save, and then I'm going to do an open, and we're going to get our, first of all, we're going to open up our start file, save it. Sample 3_11. Save. Okay. And this one, start. There's a little bigger. Okay. Once you have each one drawn to scale and at the right angle and labeled large enough again, so that when you do a screenshot, you'll be able to see the variables. Now we're ready to do the equation that they're calling for. So in this case, they are gonna start with A, subtract B, subtract C, and then add D. So I'm just going to write that equation out. Just going to copy one of the letters. It really doesn't matter which one. And they're calling their resultant J is equal to A minus vectorially, and make sure that you always use that greater than symbol, B minus vectorially C plus vectorially D. Okay, and that's going to be the order and the direction that we have to do each one in. So there are two negative or subtractions that we have here. So when we look at this equation, I'm actually going to go to the next line and we're going to rewrite it in the order that we're going to actually do it, or in the operation that we're going to do it. So we're going to say A, but we're going to add vectorially the negative, you can just put negative in front of the B, the negative value of B. So instead of like saying subtracting B, we're going to add the negative version of B. And then the same thing for C, we're going to add vectorially the negative version of C. And then we're going to add vectorially D. So the two that we need to change the direction on are B and C. Okay, so let's do that work. We're going to go up here to vector B. I'm going to double click on it and I'm going to put a negative in front of it. And I'm going to get rid of the arrowheads that are going up and to the right. And I'm going to replace it with arrowheads going down and to the left. So to make it the negative version of B, I just change the direction of the arrowhead and I relabel it as a negative B. Okay. I'm going to do that very same thing for C. So I'm going to put my negative sign in front of C. And then I'm going to delete the current arrowheads and I'm going to redraw so that they're going up and to the left. Up and to the left. And I have that negative C in front of there. Now that I have that changed, my process becomes vector addition of the negative versions. So I'm just going to tip to tail everything that I have here now in the order that we see it. So A is our first one. So we're going to put an origin at the end of A, and it's going to be at its tail. And it's going horizontal, so we don't need to add an extra one there. So now, I think I'm gonna have to move my my vector equations. I'm gonna put them up over here. So now I'm gonna add the negative version of B. So I have it in the negative version here. So to add this, I'm gonna take the tail of B and I'm gonna put it at the tip of A. And then I'm just gonna have to move my A label up to the top here. And looks like I'm gonna have to trim my line here so that my origin is not obstructing the arrowhead of B. Okay. Now I'm gonna add the negative C. So I've got my negative C here. So I'm gonna move this one and the tail of C is gonna go to the tip of A. So it looks like I've got to do another trim so that my origin doesn't cross over C. And then lastly, we're going to add tip to tail D. So I'm going to take the tail of D and put it at the tip of C. All right, so that is the right-hand side of my equation, A minus B minus C plus D. I'm going to change my layer and I'm going to draw my line going from the origin to the tip of D, which is my last arrowhead. I'm going to move D to the outside here. And then we're going to add the arrowhead here. So I'm going to do line. I'm going to make it kind of a little bit longer. Yeah. I'm going to label it. In this case, it's J. And then now I'm going to add lengths and angles. So I'm going to do the align dimension notes from this endpoint to that endpoint. Obviously, it's going to be super small. So I'm going to go to my dimension, modify, fit. I do 80. It's really small. Set as current, close. Pretty good. If you wanted to adjust it a little bit more, you could. And then I need to add in my angle. So I'm going to do an angular dimension from horizontal to, did I do it? No. From here to here. There we go. And this is 81 degrees. If we compare back to what the book has, both the magnitude and the angle, the length and the angle are matching what the book has as their result on page 57. So now all that you're going to do is this is going to be your screenshot for example 311. Okay. Now, as we look here, the next subject that we would be covering, we're going to be going to section 316. But today, this is as far as we're going to go. So the next time that we meet, we'll pick up here and we will look at vector equations. This is enough to practice before we kind of add to it. So, so what I want to do is I want to go back to the assignment number 2. Okay. And I want to just kind of give you, what you can start working on based on what we already did. Okay. So as you look here, we're going to be doing problem 20, 23, 25. So these are going to be found at the end of the chapter. Starting on page 69. Okay. Zoom out here. So in the first column here on page 69, we have graphical vector addition. You are going to be doing problem 320, 323 right here, and then 325, which is right here. Okay, they're giving you the vector equation, which means that you have to add it in that order. So for the first one, it says the resultant is equal to A plus B. So start your origin with A and add tip to tail B to it to get, and to determine what the resultant is. Then you're gonna notice for 23, they're doing these three vectors, A plus B plus C. So you have to do it in that order. And then 5, A plus B plus C plus D, and then plus E. So those are the first three problems. Go back over here. Then the next one that you're going to be looking at are going to be 32, 44, 45. Let's see what those are. So 32 is a vector subtraction. So it says for the vectors shown in 320. So 320 was problem 320. Okay, and that was the first problem that you already drew these for. Now you're going to do it as J is equal to A minus B. Okay. Then turning the page. Oh, then it goes into vector subtractions or vector equations. So I guess that's the only one that we're doing as a vector subtraction. I'm kind of surprised. Maybe just 32. All right, I guess we'll just do 32. I won't change it. So you would be able to do the first four problems based on what we've gone over up until this point, okay? So if you wanted to get started on that, these do have to be in AutoCAD form. They have to be in the format that we had just talked about, identifying the things and the labels and such, okay? So does anybody have any questions? The next time we get together, we'll then move further in chapter 3, module 2. I'm going to stop the recording here if there aren't any questions at this time.